All right, in this lesson, we are going to finally talk about the unit circle. So the unit circle is a tool that helps us determine the sine and cosine values of different angles. All right, so before we get into this, we're going to do a quick review of right triangles. We're going to look at two. They're called special right triangles. So our two special right triangles are one that has 45, 45, and 90 degrees in it, and the other one that has 30, 60, and 90 degrees in it. Now, later on in the video, you're going to see me draw a triangle inside of a circle, and we'll get to why that's important later, but for the purposes of the video right now, what you need to know is that the hypotenuse of our right triangle, remember that is the slanted side across from the 90-degree angle, the hypotenuse is going to be the radius of our unit circle. And we learned in the last video that the radius of the unit circle is 1. So I'm going to go ahead and in my notes label the hypotenuse of each of these triangles as 1. All right, now when we're talking about special right triangles, we want to be able to know what all of the sides are equal to. So if the hypotenuse is 1, I want to try, for this 45, 45, 90, I want to try and figure out what these two lengths are. All right, so a 45, 45, 90 is really nice because we have two angles that match. So we have two angles that are both equal to 45. And when we have a triangle that has two matching angles, we call that isosceles. All right, so if you want to make a note of that, this is an isosceles triangle. Okay, and in an isosceles triangle, the sides across from our matching angles must also match. So if I don't know the value of this side, I'm going to call it x, but I do know that the other side needs to be the same because it's an isosceles triangle. All right, so you have two unknowns here. You know the hypotenuse. There is a special formula you all should remember. It is the Pythagorean theorem. It helps us determine the side lengths of a right triangle. So what I'm going to do is I'm going to set up Pythagorean theorem and try and solve for the value of x. All right, so in Pythagorean theorem, remember it's a squared plus b squared equals c squared. And a and b are the two legs of the triangle, and C is always the hypotenuse of the triangle. So when I set up Pythagorean theorem, it should look something like this. You have a squared plus b squared equals c squared. That's the theory. And then we're going to replace a, b, and c with the values that we already know. So I know a is x, I know b is x, and I know c is 1. And I'm going to try and solve for the value of x. Okay, so when I do that, I have these 2x squareds. They're going to combine into 2x squared. And then I know 1 squared is 1. So finishing solving the problem, going to get this 2 over to the other side by dividing. Then I'm going to take the square root of both sides. Okay, and when you take the square root of a fraction, it's the same as taking the square root of the top divided by the square root of the bottom. And we know the square root of 1 is 1. So this is 1 over the square root of 2. Another way to write this, and the way that we will write it in this class, is square root of 2 over 2. And if you're not sure how I got there, make sure you ask me in class. But for now, just trust me. All right, so now I know my two side lengths in this triangle both need to be the square root of 2 over 2. Okay, now let's look at the 30, 60, 90 degree right triangle. So once again, I have the hypotenuse is equal to 1. And I want to try and find the side lengths down here and down here, and up here. Now you probably already noticed that I have this dotted triangle on the other side, and it looks like I just flipped this triangle over. It's just a mirror image of the other one. That's actually going to help us solve this triangle. So let me show you how. So if this triangle is just a mirror image of my original one, that means I can go ahead and label some things in this dotted triangle. This must also be 60 degrees. And this up here must also be 30 degrees. Okay, which means the total angle at the top is 30 plus 30. That's also 60 degrees. So now if I pretend for a second that this is one big triangle, in each corner of the triangle, there is a 60-degree angle. All of the angles match, right? So this triangle, even though the 30, 60, 90 is not an equilateral triangle, we know it is half of an equilateral triangle. Remember, equilateral is when all of the angles and all of the sides match up. So I could say that this is based on an equilateral triangle. All right, now you might have heard me just say it. In an equilateral triangle, if all the angles match, all the sides must match. So if this is 1, I know this side over here needs to be 1. And I also know that this whole thing on the bottom also needs to be 1. And why does that help me out? Well, because if I know this whole side on the bottom is 1, half of this side, which is what I want, should just be 1/2. So I know down here, this side is 1/2. And then I still don't know what this center length is. So I'm going to label that one as my x. And once again, I'm going to use the Pythagorean theorem. If I set this equal to a, this equal to b, and this equal to c, I can go ahead and set up my Pythagorean theorem below. A squared plus b squared is c squared. Plug in what I know. A becomes x, b becomes 1/2, and c becomes 1. Now, I want you to pause the video for a sec and see if you can solve for the value of x in this problem. Do it on your own, and I will give you the answer in 3, 2. All right, here's the rest of this problem worked out. So a couple things to point out. Hopefully you recognized that 1/2 squared is 1/4 because it's a half times a half. Another thing is when you go to subtract this 1/4 over to the other side, remember 1 whole minus a quarter, that is 3/4 or 3/4. And then finally, when you go to take the square root of 3/4, remember you take the square root of the top and the square root of the bottom. So I have root 3 over 2. So now I know my x value is equal to root 3 over 2. All right, now I'm going to get out my highlighter and I'm going to highlight all of these values here because they are important and we will come back to them later on in the lesson. All right, so before we get into the unit circle, we also need to discuss how we can use trigonometry to define distance measurements. All right, so right here we have a picture that you all should see is very familiar. You have a right triangle, and you have some unknown angle down here. We call that theta, and then each side of the triangle is labeled. All right, so we've already actually learned what sine, cosine, and tangent are. You guys learned this in IM3. So sine, cosine, and tangent, remember those are just ratios or fractions that relate the three sides of a right triangle to each other. So if you remember uh, this little acronym we learned last year, SOHCAHTOA, this tells us how to use sine, cosine, and tangent. Remember, O, H, and A stands for opposite, hypotenuse, and adjacent. So sine, it is opposite divided by hypotenuse. if I'm looking at this picture here, I start at the angle, the opposite side is A, and the hypotenuse is B. So this is A over B. Okay, cosine is adjacent over hypotenuse. So if I look at this angle, the adjacent side is C, it's the side it's touching, and then the hypotenuse is still B. And then tangent is opposite over adjacent. So if I look at my angle, the opposite side is A, the adjacent side is C. So this is A over C. Right? That should be a review from last year. But how can we use sine, cosine, and tangent, which is normally dealing with angles, how can we use it to measure the length of something? All right? So that's what we're going to talk about right now. So over here we have a circle, all right? And this is a special kind of circle. We're actually going to say that this is the unit circle. And of course, we learned in the last video that the unit circle has a radius of 1, all right? So if I was going to go ahead and label what the coordinates for this point right here would be, I would say that at that point, the coordinates are 1, comma 0. All right, remember x, comma y. And then I could go over here and I could say this coordinate is 0, comma 1. I could say this coordinate over here is negative 1, comma 0. And I could say this coordinate down here is 0, comma negative 1. Okay, that seems pretty obvious from the grid. However, what if I was to want to find the coordinate for any point on this circle? So I could put some point down here, for instance, and I could say, okay, this is going to be x and y, and I want to figure out what x and y are. All right, the beautiful thing about the unit circle is it is based on trigonometry, so it is based on right triangles. So earlier in the video I said I'm going to be drawing a right triangle inside of a circle. That's going to happen now. What we can do is we can say from the center of this circle to the point I'm trying to find, we can connect that and make that the hypotenuse of a right triangle. So how would I do that? Well, I just need to finish the triangle just like this. Here's my right triangle. And I can say, we learned in the last lesson, that there is a standard angle right here and right here. In between those two rays, there is an angle, and it is theta. I don't know what that angle is necessarily. All right, now I can use these same ratios over here to kind of help me figure out what x and y are based on whatever that angle is. All right, so if I'm thinking about just this x coordinate, all right, what leg of this triangle would represent the x coordinate? Well, I know x moves from left to right, so I know this leg of the triangle down here must be my x distance. To get up to this point, I need to move x units over, which means if I'm thinking about what leg of the triangle should the y coordinate be, well, that must be this vertical distance right here. All right, so from the center of the circle, I moved x over to the right, and then I moved y up, and now I'm at my point. And then we know the hypotenuse is the radius of this unit circle, which is 1. So I end up with something that looks like this, all right? And I can use these same concepts, sine, cosine, and tangent, to try and maybe figure out what x and y are. So let's look at cosine first, all right? So in cosine theta, remember that is the adjacent side divided by the hypotenuse. So in this triangle, the adjacent side is going to be x, and then divided by the hypotenuse is 1. Well, you all should know that x divided by 1 That's just x. Okay, we'll come back to that in just a moment. Let's talk about sine. All right, so the sine is going to be the opposite side divided by the hypotenuse. So the opposite side is y, and the hypotenuse is still 1. Y over 1, of course, gives me y. All right, so what I've just done is I figured out that there's actually another way to write coordinate points on a graph, all right? If you can figure out the angle between the positive x-axis and wherever your coordinate point is, then the cosine and the sine of that angle are going to be equal to whatever your x and y coordinates are. So I know that was a lot of words. Basically, all I want you to do is think of x comma y. Now we're going to think of it as cosine comma sine. These are the same thing. Okay, now we haven't really talked about tangent, but another cool thing to point out would be the tangent angle. So in the tangent angle, all right, we are going to do the opposite side divided by the adjacent side. So this is going to be y divided by x. And what's cool about tangent is if you look this up, it's actually true. If tangent is equal to y divided by x, and I just said y is actually sine and x is actually cosine, that means tangent must also be equal to whatever the sine value is divided by the cosine value. And that is true. That is a formula in math. All right, one last thing to point out before we move on is if each coordinate point represents cosine comma sine, that means these coordinates here also represent cosine comma sine. So if I think about, if I'm looking at this coordinate right here, all right, and I think, what is the angle of this line here? Remember, standard angle means I start on this line, and it looks like I also want to end on this line. So if I start on this line and I end on this line, I haven't moved at all, which means my angle must be 0 degrees, okay, or 0 radians. Either one is true. And what I want you to do, maybe pause the video real quick. If you put cosine of 0 into a calculator, this is why you're going to get 1. And if you put sine of 0 into a calculator, this is why you're going to get 0. And you can try that for all of these, all right? This is 90 degrees. And so the cosine of 90 degrees should give you 0. And the sine of 90 degrees should give you 1. Same thing for 180 degrees over here. Same thing for, this is 270 degrees down here. All right, so maybe pause the video, check those in a calculator. You should get these same coordinates. When you're done with that, we will move on to filling in the actual unit circle. Okay, so over on the back page, here is a blank copy of the unit circle. And this is something that ideally you will have memorized, all right? And I know that might seem like a lot, but what I'm going to do is I'm actually just going to walk you through 1/4 of the unit circle because the pattern repeats itself around the entire circle, all right? Okay, so first things first, we have lots of blanks to fill in, all right? The center circle of blanks, those are radian measurements. The middle circle of blanks, those are degree measurements. You can kind of see the degree symbol. And then the outer circle of blanks, those are coordinate points. So I'm going to focus in on just quadrant 1, this top right wedge of the circle. And I'm going to go ahead and fill in everything I already know. Okay, well, I know that this coordinate right here is 1, 0. I also know that this coordinate right here is 0, 1. I can do some angle measurements now. Let's do degrees since I'm used to those. This is 0 degrees, but remember I could go all the way around the circle and end up right back at the same spot if this is also 360 degrees. I know this one up top must be 90 degrees. And then I can kind of reason my way through what these might be. This one looks like it's halfway between 0 and 90. So this is 45 degrees. In fact, all of these are going to be some 45-degree offset. This one right here, it's in between 0 and 45. This one is 30 degrees. I'll just tell you that. And then this one right here is 60 degrees. All right, so before we get into coordinates, let's real quick make sure we know how to do the radians for this. We learned in our last video that 0 degrees is also 0 radians, but that a full 360 degrees is the same as 2 pi radians. Right, so a full way around the circle is 2 pi. We also know that a quarter of a way around the circle is pi over 2. All right, now I want you to pause the video right now and see if you can figure out the radian measurements for these 3 degrees right here. I will give you the answer in 3, 2, 1. Okay, so you should have had that 30 degrees is pi over 6 radians, 45 degrees is pi over 4 radians, and 60 degrees is pi over 3 radians. If you don't remember how to do that or you struggled with that, remember there are 2 ways to think about this. One, you could take your degree, divide it by 180, and then multiply it by pi. Another way you could think about it is if 30 degrees is a portion of the circle out of 360, I know 30 times 12 gives me 360. So 30 is 1/12 of the circle. So all I would need to do is take 2 pi and divide it by 12, and I'll get pi over 6. In this case, I would take 2 pi and divide it by 8. 45 is an eighth of 360. And in this case, I would take 2 pi and I would divide it by 6, because 60 times 6 gives me 360. All right, very good. Let's talk about the coordinates here. Now, hopefully you recognize that uh, these angles are not random. They're very intentional. We have a 30-degree angle, a 45-degree angle, and a 60-degree angle. And at the beginning of the unit, we talked about, or not the unit, the lesson, we talked about a 30, 60, 90-degree right triangle, and we talked about a 45, 45, 90 right triangle. Okay, that was intentional. That's so that those triangles are going to help us figure out what these coordinate points are. So if I imagine for a sec that there is a triangle right here up to this point, I know that this must be 30 degrees, all right? And if I go back to my diagram, this is the x distance of my triangle. This is the y distance. And if I go back up to my diagram, I learned that the side across from 30 degrees must be 1/2, and the side adjacent to 30 degrees must be √3 over 2. So when I go back down to my unit circle, the side across from 30 degrees is 1/2, so the y coordinate must be 1/2. The side adjacent to 30 degrees must be my x coordinate. That must be √3 over 2. And I can do that for each of these angles that I'm trying to find the coordinates for. So if I look at this one, in this case, this is a 45-degree angle. So the side across from 45 is actually, this side and this side are the same, remember, because it's an isosceles triangle. So my x-coordinate and my y-coordinate are both going to be, if I look back at my diagram, √2 over 2. All right, and then finally, if I look at my 60-degree mark here, it's the same as if I draw this triangle and I say this green angle must be 60 degrees. If I look back up at my original diagram, the side across from 60 degrees is root 3 over 2. The side across from 30 degrees is 1/2. So across from 60 degrees, that's my y coordinate. This is root 3 over 2. And then right next to 60 degrees, this is my x coordinate. This is 1/2. All right, now a couple patterns to point out to you before I turn you loose so that you can see if you can figure out the rest of the circle. First of all, the 45-degree marks, those coordinates are always going to match. They're always going to be the exact same. They're always going to be root 2 over 2, comma, root 2 over 2. Very good. Now, the 30 and the 60-degree ones, those coordinates just switch spots, right? And you kind of have to think through. I always try to remember, all right, at the 30-degree mark, it looks like I've gone further in the x direction than the y direction. So that's how I know the root 3 needs to be first. It needs to be my x coordinate because it's bigger. For the 60-degree, it's the opposite. I went really tall this time. So it looks like I went up further than I went out. So now I know the root 3 needs to be in the y coordinate. But those two are just the reverse of each other. Okay, I'm going to let you pause the video and fill out the rest of the unit circle. See if you can get all the degrees, all the radians, and all of the coordinate points. Before you do that, I'm going to give you one last hint. Each quadrant has a little trick to kind of help you with your coordinates. So quadrant 1, you should know that all x values and all y values are positive. In quadrant 2 over here, it's going to be the exact same numbers, but some of them are going to be negative now because now we've crossed over to the left. So now all of my x coordinates should be negative and my y coordinates are still positive. In quadrant 3, both my x and my y are negative. And then in quadrant 4, I'm on the right side, so my x is positive. Oops, but I'm on the bottom, so my y is negative. All right, so go ahead and pause the video, see if you can fill out the rest of the unit circle. I will give you the solutions in 5, 4, 3, 2. All right, so here are all of the values filled in. A couple things I want to point out to you before we end this lesson. First of all, I kind of color coded it for you so you can see the ones that match, but the ones that are directly across from each other are always going to have the same coordinates. So that's something you can maybe reason through. All right. Okay, and then the other thing I want to point out is remember each of these coordinates represent cosine, comma, sine. And so if you were to, this is in fact how I want you to end this lesson, if you were to pick any one of these angles in degrees, or if you set your calculator in radian mode, if you were to pick any one of these radians, if you, for example, take the cosine of 135, your calculator will spit out the negative value for whatever square root of 2 divided by 2 is. Okay, that's it for the unit circle.